My name is David Wallance. I'm with FXFOWLE Architects. I suspect that there are a lot of engineers in the audience, so you're going to hear an architect's view of the future of volumetric modular construction. This is a problem I started working on about 10 years ago with a startup firm called Global Building Modules, or GBM. And what we set out to do was, rather than to design specific buildings using modular technology, we set out to design what I would call a delivery system for producing buildings that are able to be manufactured at very large scale, very large volume, to meet the needs of a rapidly urbanizing planet. So I like to juxtapose images of the conventional building site with images of high-tech advanced manufacturing. The slide on the left, really the process of putting a building together on the building site hasn't changed very much for thousands of years. You can go back and look at old Renaissance paintings of construction sites, and you see primitive cranes. You see groups of workers standing around trying to figure out what to do next. They're working out in the weather under conditions of heat, cold, wind, rain, snow. In a three-dimensional workplace, very difficult to coordinate. Productivity is stagnant over the last 50 years. The productivity on the construction site has actually declined a bit, whereas in the manufacturing sector, productivity has increased over the last 50 years by about 250%. The challenge we face is that the world's urban population is projected to increase by another 2.5 billion inhabitants by the year 2050. And if you assume 5 persons per household, that means that over the next 35 years, we need to generate 500 million new housing units, urban housing units, and actually an even greater number of replacement units for housing that is presently substandard. That works out, if you do the arithmetic, to 1 housing unit virtually every breath you take, virtually every 2 seconds. There are roughly 70 developing countries with 4 billion people that want to achieve Western-style standards of living. They want to have cars. They want to have comfortable dwellings. And the result of that is that because of the high cost of multi-story urban construction, those people are adopting American-style suburban sprawl. The urban land cover is increasing at twice the rate of urban population growth, which has dire environmental consequences if over the next 35 years that upwardly mobile population produces the kind of suburban development that we've done here in the US. Now, we hear a great deal about how prefabrication and modular architecture and construction in particular is the answer to this problem. But if you actually look at the state of the industry, the modular industry is not equipped to effectively respond to the need. By 2017, the modular industry will be putting out 829,000 units. And if you project forward to 2050, assuming a modest annual growth rate compounded, about 3.5 million units, which sounds like a lot. But if you do the arithmetic, the need for 500,000 units, 500 million, pardon me, 500 million units of housing by 2050, compared to the projected ability of the modular industry to deliver of about 3.5 million. That's less than 1% of the projected need. And so this brings me back to the thesis that my colleagues at FXFOWLE and at Global Building Modules have arrived at, which is the problem of modular construction is not the problem of how do you build a modular building in a factory. It's the problem of transportation. The conventional modular industry is wedded to the premise that bigger modules are better. Bigger modules means fewer trucks that have to roll down the highway, fewer crane picks, fewer mate lines to patch up in the field after everything is put together. But the unintended consequence of this commitment to oversized modules is that the conventional modular industry can't transport beyond about a 200-mile radius before it becomes uneconomical. And in fact, the modular industry sells on the time savings, not on the cost savings that they can achieve even within that 200-mile radius. What this does is it traps these companies in small markets with high overhead. They're subject to business cycles. And so these companies barely hang on, working at a fairly low level, maybe up to about $40 or $50 million of gross revenue a year. They can't invest in R&D, they can't invest in advanced manufacturing, and then they sometimes go out of business, as happened with one of the major steel frame modular manufacturers in the New York region, Cullman Industries, which went out of business in 2011. So if we look at the transportation side of the problem, the answer is hiding in plain sight. It's the intermodal transportation system that moves shipping containers around the world. And what we're interested in is not the shipping container itself. We're interested in intermodal transportation. The intermodal shipping system is massive and global in scale, and it costs, if you look at it in terms of construction costs, if a shipping container is about 320 square feet of floor area, it costs about $12 a square foot to move a shipping container from Shanghai to New York. And the annual global trade in shipping containers is in the 684 million TEUs. That's an acronym for 20-foot equivalent units. Most shipping containers today are 40 feet long, so that's actually about 340 million regular shipping containers. That's the equivalent in square footage of 97 million dwelling units. And if you remember the 500 million units that are needed over the next 35 years, you can see that now we're talking about the kind of scale that we need to achieve in order to meet the need for multi-story urban housing. So I'm going to show you some images that touch on rather lightly on the technology that we've developed. There's a great deal that lies behind these images. We've worked with Leslie Robertson and Associates as our structural engineer. So there's a lot of structural engineering that's behind this. The shipping container as an artifact is actually beautifully evolved to its purpose. It's one of those, what Le Corbusier called an object type, an object that through use and adaptation and evolution achieved its level of, a certain level of perfection. But it doesn't work very well for building construction. It's got plywood floors. It's got lots of material that one needs to cut away in order to make interconnectable units that create rooms that are larger than a shipping container. A lot of the value-added material, like the doors, has to be taken away and either recycled or somehow reused. So what we were interested in was the 8-foot by 40-foot dimension and the 8 corner nodes that are designed for intermodal automated handling. And so we call what we've done by stripping away all of that extraneous material down to its geometric properties, we call that the volumetric unit of construction, or VUC. And then we proceed to use shipping container manufacturing technology to build a module that's purpose engineered for building construction. It's optimized for floor stiffness, for spans, and we only put the corrugated material in our VUC where we want it, either because that's behind a panel of opaque facade or because it's needed for shear stiffness. And then we seal those modules up with reusable modular protection panels, and to a logistics company, it moves seamlessly around the world on the intermodal system, just like a shipping container full of consumer electronics. We clad the modules with rain screen facades. Cladding is shipped separately. It won't go well on an overseas voyage. So we ship cladding to a staging area near the job site. We attach facade panels to the modules before they're trucked the final leg to the job site, and then the modules are craned onto the building with facades in place. Now, one of the questions that frequently comes up when I talk about this system is, well, are we going to produce the same building, millions and millions of the same building all over the world? Well, no. The idea is that what we have is like, in effect, the analogy to the iPhone. I like to think of the volumetric unit of construction as the operating system. And I expect that GBM will start licensing that operating system to third-party app developers, architects, product manufacturers, industrial designers will design components, whether they're facade components or interior fit-out components, to adapt to the basic standard dimensions. These will be pre-engineered to work like a plug-and-play system, balconies, sun shading systems, and the like. And interior fit-out can also be developed along the lines of apps. I recently read that the Porsche studio, the automobile design studio, has partnered with Bafi to design a line of kitchen cabinets. And so the European kitchen system is actually a perfect idea about volumetric modular writ small. The European kitchen is based on a 30-centimeter module, and yet these manufacturers have come up with kitchens that are objects of consumer desire. These are not monotonous or downscale in any sense of the word. So as part of our development, we looked at a variety of unit types. This was a test fit for a studio and one bedroom. A studio over there and a one bedroom here. And one of the things that you'll notice is that we're organizing our modules parallel to the facade plane. We're not necessarily plugging them in perpendicular to the facade plane. We can do them perpendicular to the facade plane as well, as is shown in this one-bedroom unit. We can do duplexes with prefabricated internal stairs. And then moving to the building scale, we looked at how VUCs can be integrated into buildings based on 4 typologies: row housing, mid-rise perimeter block, high-rise slabs, and high-rise point towers, and began to develop specific modules for core systems: vertical transportation, corridors, risers, and lateral runs in corridors. Last year, we did a study for a 500,000 square foot housing mixed-use complex in Philadelphia that was comprised of 1,600 of these identical 8-foot by 40-foot VUCs in 3 typologies. We have row housing, mid-rise, and towers on top of a conventionally constructed retail podium. One of the advantages of our system is that it's extremely lightweight, so when one is building on top of a conventional structure, there are also cost savings associated with reduced structural requirements. So, in a flat world, there are 3 things that matter above all else. Number 1 is scale. But wait, I can't remember what the other 2 were. Oh, yeah, that's right. Number 2 is scale. And number 3 is scale. That's the most important thing. If you look at the manufactured housing industry, the good old single-wide trailer, the average price of a single-wide is $45 a square foot. It has a kitchen, a bathroom, electrical systems, plumbing, air conditioning, an aluminum skin, a steel chassis, rolling stock. All of that factory made for $45 a square foot. My colleague, Jamie Bacchus, did some analysis of urban versus suburban construction costs. And what we found was if we can start bringing the cost of VUCs down, let's say down to $65 a square foot, allowing for transportation, and $90 a square foot for on-site costs, which we've verified on that Philadelphia project. If you look at all-in costs for construction, including cost of land, the graph is showing is showing a range of land costs. The green is land at $1,000 a square foot. The blue is land at $20 a square foot. And as you increase density, if you can bring these costs down, you can start to bend the cost curve to the point where multi-story urban construction becomes less expensive than stick-built suburban construction. And we think that that's what needs to be done in order to start drawing people back to cities, back to dense urban living. And the answer isn't micro units. The answer isn't making 300 square foot units for college grads to live in for a few years. The answer is to build large, commodious, high quality, multi-story urban housing that will bring middle-class families back to the city. We also think very deeply about the sustainability angle. Clearly, factory processes are far less wasteful, far more efficient than on-site practices. Overseas transportation is 10 times more energy efficient and produces 1/10 of greenhouse gas emissions of trucking on the highway. And urban density is inherently more green than suburban development. Even if you were to build a net zero suburban house, as soon as you take transportation into account, the overall energy footprint of suburban development is 40% less efficient than urban development. This is a study that was done by the Jonathan Rose companies to show how location efficiency is is really the big story. Once you add on all of that technology, photovoltaics, super insulated walls, you gain another 16%. But inherently, it's dense urban construction that gets you the biggest cost savings for the least amount of money. I'm often asked about the green attributes of the VUC itself. So its embodied energy is about 17% less. It uses no poured-in-place concrete. It's entirely a steel-framed, steel floor system. Its weight is about 1/3 of conventional steel and concrete. We did a comparison to a steel and precast plank building and found that we were about 1/3 the weight. Transportation, if you look at the tons of CO2 per mile of transportation, the amount of CO2 rather per ton mile of transportation, because so much of the transportation is overseas, which is 10 times more efficient, it's actually 24% more efficient to transport VUCs than to build a building according to the LEED standard of 500-mile radius procurement, even if that LEED building were 100% procured within that 500 miles. I like to talk about a global vernacular. And I use the phrase, the big grid. It's the idea that we'll have this global network of connected app developers working on social media platforms, working on a shared software system. The idea that ultimately we'll develop software that allows the architect or the app developer to work on buildings using the GBM system, borrowing BIM components from a central database, and that database will be constantly expanding as new apps are added to the system. That BIM model that's being created has a real-time dashboard. It allows the designer to see on the screen the cost of the building that he's designing, he or she is designing. It allows the designer to see the CO2 impact in real time of the building that they're designing. And ultimately, that BIM model will drive a back-end enterprise software that we envision because of the standardization of the operating system and the rigor with which it's adhering to a set of preset dimensions. It will be able to drive advanced manufacturing and ultimately achieve the real promise of industrialized modular construction.